What's up, people? Welcome to the session. How are you guys doing? Welcome, welcome, welcome. Let me just enlarge my screen. What's up? Hello, hello, hello. What is up, people? I hope all of you guys are doing good. I hope you're having a fantastic, fantabulous day so far. My name is Anoop, and this is Vedantu, and a very warm welcome to all of you guys out there. Hoping you're having a wonderful evening, right? So, people, what we're going to do today is going to be very, very simple. What we're going to do is basically go through some of the most top expected questions for your term 2 examinations. Now, I know it's really not a good time to study physics because your math exam is right around the corner. Only a couple of days for your math exam. I believe tomorrow is your math exam, if I'm not wrong. So, I wish you guys all the very best of luck for that, right? For all the students who are going to give you a math exam, go ahead, chal kar fold the paper, right? Break into 1,000 different pieces. Now, I know it's not a good time to study physics, but still, chalta hai. 1 hour of break from math is still good. So, very quickly, I'm going to keep it very short and sweet. We'll just go through some of the most expected questions for your term 2 examinations. All right. So are you people ready for this? Put it down in the chat box. Give me a, oh yeah. Hi Simran, what's up? Hi Veena, what's up? Hi Nightbot. What is up, guys? Welcome, welcome, welcome. So are you guys prepared for your math exam, by the way, people? All good for your math? I know. Arey, don't stress yourself out so much. I know math is a beautiful subject with beautiful numbers and beautiful formulas and all that. But all I want to say is this: stay calm, relax yourselves a little, because at the end of the day, you have done everything possible for the past 1 year, right? Everything that is possible. You have given your very best. You've given your 100% for your preparations. So all you need to do is stay calm and stay positive. All right, that's all you need to do. All right, sure, Simranji, absolutely. Why not? All right, so that's it. Let's get into the topic, people. Let's get into the session without wasting much of your valuable time. I'm going to keep it very short and sweet, as I told you before. So some of the most expected questions is what I'm going to go through. Again, very quickly, we'll go through some of these questions again, so that you have some break from your math exam. But at the same time, I'll make sure that I don't eat up so much of your time, because you need to prepare for your math, right? Okay, so the first question is quite an easy one, people. Here's the question. Write any one application for each of the following. The first one is Fleming's left-hand rule. Where do you use Fleming's left-hand rule? And the second one is Fleming's right-hand rule. Where do you use Fleming's right-hand rule? Bacha question. This is probably the best stress buster for your math exam. Okay, tell me, guys, where all do we use Fleming's left-hand rule? Any place that you can think of? Arey Simranji, hi Angel, what's up? All the best for your math exam, by the way. Absolutely right, people. Basically, your Fleming's left-hand rule is used in motors, your DC motors in particular. We use Fleming's left-hand rule to predict in what direction the armature coil or the conducting coil is basically going to rotate. That is the answer for the first question. For the second one, where is Fleming's right-hand rule used? Exactly, AC generators. Absolutely correct. So in AC generators, that is your alternating current generators, which is apparently not a part of your syllabus, but still this is some place where you actually use Fleming's right-hand rule as well. All right, is that clear, people? Can I get a quick yes, so that we can move ahead to the next question? All good? All the people watching it on the session, all good? Awesome. Now, thank you, guys. Brilliant, guys. Absolutely fantastic. Let's go on to the second question then. Here is the second question for you people. Draw a diagram to show the pattern of magnetic field lines through and around a current carrying solenoid. If you have a solenoid, what does the magnetic field lines look like around the solenoid? Second question is, list two factors on which the strength of the magnetic field produced by a solenoid depends on. And lastly, what is the effect of placing an iron core in a solenoid? Beautiful question. I believe the first question is very, very simple. The first part is basically all you need to do is remember the bar magnets. It's as simple as that. Your magnetic field lines of of a solenoid is very much similar to that of a bar magnet. So it's absolutely going to be super duper easy. All you have to do is draw a solenoid and then draw the magnetic field lines around it. And inside, basically, the magnetic field lines are going from north to south. So you can take any of them as the north pole and the other one as the south pole. So I'm going to consider this as the north pole and this as the south pole. So inside, on the other hand, the magnetic field lines would be moving in the opposite direction. So that's all you need to show and you're good to go. Super easy question, very straightforward and very, very simple. Second one is list two factors on which the strength of the magnetic field produced by a solenoid depends on. What is the strength of the magnetic field depends on? Super easy. Exactly, Beenaji, exactly. So the two factors, there are three factors in general which based on which the strength of the magnetic field depends on. The first one is the number of turns. How many number of turns, that is a deciding factor. The more the number of turns, the greater the length of the conductor. The greater the length of the conductor, the stronger the magnetic field. That's the first one. The second factor that it depends on is basically the magnetic field itself. So, the current flowing through the conductor. My bad. The current flowing through the conductor. So, more the current flowing through the conductor, the greater the strength of the magnetic field. So, these are the two important factors on which it depends on. Basically, they are talking about the Lorentz force over here. So it's dependent on, sorry. All right, my bad. I don't know. I'm also thinking about a math exam and I've also lost my mind. All right, two factors magnetic field depends on is the number of turns and the current flowing through the conductor. Sorry, that happens. Sometimes even we also get lost. All right, third question. What is the effect of placing an iron core in a solenoid? Now, the thing is very simple, guys. If you were to place an iron core inside a solenoid, what would happen is that the iron core also gets magnetized. And the minute it gets magnetized, the strength of the magnetic field would also increase along with it. In other words, you would have a stronger magnetic field if you were to place a soft iron core into the solenoid. As simple as that. All right. Is that clear? All good? I know, Miss G, I know. So can you please tell what is acceleration, Harsh? Acceleration is nothing but rate of change of velocity. In simple words, da. But yeah, good question, a good question. Coming to 10th standard, I like, asking 9th standard syllabus. Okay, you're from 9, no? Okay, then makes sense. All right. Okay, next one, guys. Super easy question again. Probably one of the most repeated kind of question that you can see, maybe they might ask you in different formats, but it's very, 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 common. This kind of question is very, very common, and it's something that you can definitely expect in your term 2 examination. The question is, how can you arrange 3 resistors of 2 ohms, 10 ohms and 5 ohms such a way that you're getting a total resistance of 1 ohm, less than 1 ohm, and also you're supposed to find out what is the equivalent resistance of that combination. Now, first thing first, you need to make sure that you connect them in a manner where the resistance is less than 1 ohm. That is one thing. Now, if it is less than 1 ohm, what is it going to be? What is the equivalent resistance going to be? That is the question. Let's go. I know, Aisha. All the best for your math. This is going to be a chill session for your, so you get a break from all the math you've been doing. So don't worry about it. I won't take much time. We'll just, it's sometimes good to take a break once in a while, right? So it's consider it to be a session like that. All right. Don't take too much tension. Don't don't break your head over it. Relax. I know math is considered to be one of the most toughest subject. Honestly speaking, even it was difficult for me. It was very difficult for me as well. But you'll get through it. I'm sure of that. All right. Don't worry. Thank you. Thank you. A lot of work went into it. Exactly. All right. Okay. So how do you connect those people? As simple as this. All you have to do is connect them in parallel. That's all. All you have to do is connect them in parallel, because in parallel connection, the equivalent resistance will always be less than the individual resistance. So 1 by R equivalent is going to be 1 by 2 plus 1 by 3 plus 1 by 5. So if you were to, find out the LCM, I'm going to take it as, I'm going to take these two and find out the LCM for this first. So it's going to be 2, 3, 3, 2. So that's going to be 3 plus 2 whole divided by 6 plus 1 by 5. This can be written as 5 by 6 plus 1 by 5. Again, find out the LCM over here. I believe 30 is the LCM. So this is going to be equal to 25 plus 6 divided by 30, which is going to be equal to 31 by 30. Now remember, it is 1 by R equivalent. Now reciprocate it to R equivalent, which would be equal to 30 by 31, which when you calculate, you would get it as 0.97 something, if I'm not wrong. Again, if my calculation is correct, it'll be something around that. Let's just check the right answer. Yes, it's going to be 0.97. Yes, that'll be the answer. Got it, people? Super easy. That's all right. I know you want a different color. Why not? Why not? Q&A, Q&A. Can you see this? Is it possible? I mean, can you guys? Okay, let me just increase the thickness of it. I think that will be better. Now it is better, no? Let's go with that itself. All right. So the answer for this question, very, very simple. It's going to be 0.97 ohms. Because why? Because in parallel connection, the individual resistance would always be greater than the equivalent resistance. Or in simple words, the equivalent resistance will always be less than the individual resistances. Next question. Again, a for sure, damn sure question is this. What would be the equivalent resistance for a certain connection? Now, this is definitely going to be there. I'm not saying the same question will be there, but the similar type of questions. So the more circuits you're looking into, the more circuits you practice, the easier this is going to get. So with that said, find out what is the equivalent resistance in this scenario where you have several resistors connected in series, in a combination of series and parallel connection. The question goes like this. So please read it carefully. Please look at the diagram carefully and then decide what you would like to do. All right. So yes. To approach this question, guys, the first thing I would request you to do is basically look at which of them are connected in series and which of them are connected in parallel. So what I would suggest you to do is, you clearly, if you see over here, let me just okay, you can see this, that these two resistors are connected in series. So first of all, solve for that. So I would, it would be better if you could name it. It makes it a lot more easier. So I'm going to name this as R1. I'll name this as R2. I'll name this one as R3. Maybe this one is R4. Maybe this one is R5. This is R6 and this one is going to be R7. So I'm just going to go clockwise. Now the naming is totally left to you guys. It is up to you. You can do it whatever way you want. Now with that said, first thing first, I am going to solve for this. So I'll just take it as R23. So R23 is equal to 1 plus 5. This is R3 is 5 ohms. So this is going to be equal to 6 ohms. So keep that as it is. Now if you look carefully, you can see that R6 and R4 are in parallel. So solve for that also then. So 1 by R64 is equal to 1 by 6 plus 1 by 3. Again, solve, find out the LCM. So 3 2s are 6. So it's going to be 1 plus 2 whole divided by 6, which is equal to 3 by 6. So R64 is equal to 6 by 3, which is equal to 2 ohms. So this whole thing is 2 ohms. Now once you solve for that, now you can see that R5 and R34 are in series. So solve for that also then. So R564 is basically equal to 2 plus 2, which is equal to 4 ohms. Now that you solved it, this is what your new circuit looks like. You have one resistor over here and you have this one right here. This is also in parallel. So this is going to be R23, which is basically equal to 6 ohms. This is going to be equal to 4 ohms. And this one right here is basically 8 ohms, right? So now solve this as well. So you can see that these two are in parallel. So solve for that also then. Again, guys, I'm just going, I'm not drawing the diagram, because one thing is you have already seen this question. Honestly speaking, I have done this question in the previous sessions also. So I'm just going to go through it quickly. And on top of that, I want to do it fast so that you guys can spend a lot of time on your math exam. All right. So that's why I'm going a little fast. Please, forgive me for it. It's just that I want you guys to prepare for your math exam as well. All right. So with that said, we know that those two are in parallel connection. So solve for that also next. So it's going to be 1 by R564 23. All right, that's a long one. So R5623, R56423 is equal to, right, sorry, my bad. Where's the question? All right, this is the question. No, okay. Wait, where's the question? This is the question. Okay, so that's going to be what? What is the name? This is 2, 3. This is 4, 5, 6. Sorry. So solve for that. R23. Yeah, so you can just keep it as it is. This is equal to 1 by R23 plus 1 by R564. This 1 by R23 is basically what? That is 6 ohms. So that's going to be 1 by 6. My bad. 1 by 6 plus it's 1 by 4 if I'm not wrong. So 1 by 4. Again, find out the LCM over here, get the answer. It's a long procedure. Find out the LCM over here. I think you can go with, how much is it? 30, no, 12. So 4, 3, 12. 6 into 2 is 12. So it's 2 plus 3 whole divided by 12, which is equal to 5 by 12. This is equal to 12 by 5. 5 to 10.5420. So this is going to be 2.4 ohms. Now that you solved it, all of them are in series. The next step you have to do, all you do is see that this is how it's connected now. So they are all in series. Solve for that and you're good to go. So that's basically how much? It is basically 4 plus 2.4 plus 8. So that is going to be the final answer, which is basically how much? 8 plus 4, 12. Total plus 4 is 14. So it's going to be 14.4 ohms. That's the answer. All right. Long procedure, but it's a simple question nonetheless. It's not that difficult. Honestly speaking, it's really not that difficult. It says that it's a really long procedure. So you need to be up for the task. Make sure you spend enough time on that. All right. All good? Alright, awesome, Catty and G. Thank you. Alright, moving on a little bit more. That's all. We'll do a couple more questions and we are good to go. Again, math exam is tomorrow, so all the very best for that. Alright, here's another one. A coil of insulated copper wire is connected to a galvanometer. What will happen if a bar magnet is pushed into the coil first, withdrawn from the coil, or from inside the coil, and held stationary inside the coil? Now, if you have an insulated copper wire, basically a solenoid, which is connected to a galvanometer, right? And you're bringing a bar magnet, initially what you're doing is that you're pushing the bar magnet into it. Now, the minute you push the bar magnet into it, what is going to happen? There is going to be current induced in it. There's going to be an induced current. Current is going to be induced in it. And because of that induced current, there will be a deflection in the coil, in the galvanometer. There's going to be a deflection in the galvanometer. The needle inside the galvanometer will deflect. Once again, when you withdraw the bar magnet from the coil, again there's going to be a current induced. Again there will be a deflection, but this time the deflection will be in the opposite direction. That is the difference. All right. So initially, let's say that the deflection, the needle inside the coil went towards the right. Since you're taking the magnet away this time, the deflection will be towards the left. So it will be in the opposite direction. That is the only difference. Lastly, what would happen if you keep the magnet stationary? Simple, nothing, no change at all. Because in order for you to have electromagnetic induction, there has to be a changing or moving magnetic field. So the minute you stop the magnet, there's going to be no more deflection and the galvanometer's needle will come back to zero. That's it. Exactly, Angel G. That's all. EGPG, guys, EGPG. But yes, again, you can definitely expect questions like this in your boards as well, because electromagnetic induction is a very, very, very important topic. All right, sixth question. Here's another one. Mention the factors on which the direction of force experienced by a current carrying conductor placed in a magnetic field depends on. The force, basically they're talking about the Lorentz force now. Under what condition is the force experienced by a current carrying conductor placed in a magnetic field the maximum? And lastly, a proton beam is moving along the direction of the magnetic field. What force is acting on the proton beam. Let's start with the first one. All right. What factors does the direction of force experienced by a current carrying conductor depend on? What are the factors? Exactly, Carrie Henry. So the force acting on the Lorentz force basically depends on two factors. The direction, basically, if you talk about the direction, there are two factors on which it depends on. The first one is the magnetic field, the direction of the magnetic field. If the direction of magnetic field changes, the direction of force experienced by the conductor would also change. Secondly, the direction of the current as well. Because if you change the direction of current, the direction of force experienced by the conductor would also change. And that is exactly what is indicated by your Fleming's left-hand rule, where your index finger shows the direction of magnetic field, your middle finger shows the direction of the current. Simple, right? Okay, next one. Under what condition is the force experienced by a current carrying conductor the maximum? Exactly, Niveda. Exactly. Force experience, the Lorentz force experienced by a conductor is maximum when the magnetic field and the current is perpendicular to each other. Perpendicular in the sense it is at 90 degrees to each other. That is when it's going to be maximum. When current and magnetic field are perpendicular to each other, that is when the force experienced by the conductor is maximum. Lastly, if a photon beam is moving along the direction of magnetic field, what is the force acting on the photon beam? Again, a very simple question. Let's go people. Bacha question da, chalo ji, jaldi karo. What is the direction of, what is the force acting on a photon beam if it is moving in the direction or along the direction of magnetic field? Let's go. What is it? Come on da. Bacha question. The answer is 0. There will be no force at all. Why? Because if magnetic field and the current are in the same direction, then the angle between them is 0. So according to the formula, F is equal to BIL sine theta, and sine 0 is what? Sine 0 is 0. So the force will also be under 0. Got it? Exactly. That will be the answer. All right, please remember this though, it's very, very simple, but it's also something which a lot of people get confused in. So please don't forget that. All right, next one, people. 7th question. Let's do it very quickly so that you have enough time for your math preparation. Here's another one. Two lamps, one rated at 100 watts, 220 volts, and another at 60 watts, 220 volt, are connected in parallel to electric main supply. Find the current drawn by two bulbs from the line if the supply voltage is 220 volts. What a brilliant question. Let's try to find out. It's a very simple question. I'll tell you why. Two lamps, one rated at 100 watts, 220 volt. All right, there's another one. So let's write on the power. So first one, the power is 100 watts and the voltage is 220 volt. For the second one, the power is 60 watts and the voltage is 220 volts again. You need to find out what is the current drawn by both the bulbs which is connected to the main supply. Very simple question. I'll tell you why. Now for the first one, guys, for the first bulb, right, or the first lamp, we know that power is equal to voltage into current. So what is current equal to? Power by voltage. Simple. So for the first one, it's going to be 100 divided by 220. 0 gets cancelled, 2 5s are 10, 2 11, 22. So that's going to be basically equal to what? 5 by 11 ampere. This is the current drawn by the first one. Now again do the same thing for the second one as well. Again, I is equal to P by V, which is equal to what? 60 by 220 now. 0 gets cancelled, 2 3 6, 11. So it's going to be 3 by 11 amperes. Simple. So what is the total current? You need to find out what is the total current drawn from the main supply. So total current, I total, is equal to I1 plus I2, which is equal to 5 by 11 plus 3 by 11, which is equal to 8 by 11 amperes. That will be the answer. Now if you want to convert to decimal points, absolutely fine. You will get the answer as, 0.727 ampere. That will be the answer. If you want to convert to decimal points, that's also absolutely fine. If you want to keep it like that, that is also perfectly fine. There's nothing wrong in it. 8 by 11 amperes, or you can also write it as 0.727 amperes. That's it. All right, so that is the answer for that question. With that said, the last question for today, people, this is going to be a case study based question. So let's quickly go through this one as well. The question is, read the paragraph and answer the question. An electric motor is an electrical machine that converts electrical energy to mechanical energy. Most electric motors operate through the interaction between the motor's magnetic field and the electric current in a wire. Winding to generate the force, all right, winding to generate force in the form of torque applied on motor's shaft. Okay, now basically they're talking about electric motors. I'm guessing you've already figured that out. The question is, name few devices where electric motors are used. Can you please put it down in the chat box? Any examples, day-to-day examples where you're actually where you actually see the use of an electric motor, please put down in the chat box right now. Come on guys, quickly. Any examples that you can think of? Few examples, at least 2 to 3 examples would be absolutely fine. All right, go ahead, quickly. Come on. Few examples that you can think of. Yo. Washing machine, yes, absolutely wonderful. The washing machines, definitely they do use motors inside of it. Washing machine, yes. Any other example? Fan is a very good example, which is one of the most common things, especially when summers are right around the corner. Fans. You can also mention hair dryers. Hair dryer also use motors. You can talk about toys. Toys also use electric motors. Tons and tons of examples. You'll find brilliance of examples where we use electric motors these days. Second one, in electric motor, magnetic field is produced by what? What is the one part in an electric motor which is actually producing the magnetic field in an electric motor? AC, yes. Fan, fridge, tons and tons of examples you can give. All right, second one. In an electric motor, magnetic field is produced by what? What is the one, or what is actually producing the magnetic field? Let's go. Exactly, the permanent magnets. Such an easy question. The permanent magnets. Now, in the case of your DC motor, the one that you've seen in your textbook, it's permanent magnets. But in our real lives, like in our day-to-day life, we also use temporary magnets, or you can say electromagnets as well, all right? So electromagnets or your permanent magnets are the ones that is actually producing the magnetic field. All right, next one. The direction of magnetic force on a current carrying conductor placed on a magnetic field is given by what? The direction of magnetic force on a current carrying conductor placed in a magnetic field is given by what? I know. Good question. It's just for a break. That's all, nothing else. Iron Tech, it's just for a break, because I'm pretty sure a lot of your brains are already cooked from math exam because of your math exam. So this is a small break. That's all. Exactly. Now, Fleming's left-hand rule. So in your Fleming's left-hand rule, Fleming's left-hand rule is the one that is used. In your Fleming's left-hand rule, the index finger is the one that actually mentions or tells you or indicates the direction of the magnetic field. Lastly, what is the moving part of the electric motor called as? Electric motor called as. What is the moving parts of an electric motor called as? Very simple question again. What is the answer for that? Very quickly, guys. Come on. Quickly, jaldi. What is the moving part of an electric motor called as? Bacha question again. What is it? What is it called as? Simple question. Exactly. Rotor. That's all. They're called as rotors. That's it. Stationary part is called as stators. Rotatory parts or things that move are called as rotors. All right. So that's all, guys. That is all for today. I am not gonna extend it. I am not gonna drag the session. I'm gonna keep it short and simple as promised. So I'll take leave now. But before I leave, again, I would like to wish you guys all the very best of luck for your math exam. All the people who are going to give your exams tomorrow for your math term 2 examinations, all I would like to add on or say is be confident, right? You are prepared. All you need to do is be confident and be stern, and do not second guess your answers. I'll honestly tell you my example. I was someone who was very much, very much doubtful of of the things that I used to write in my board exams. Honestly speaking. So what I used to do is that I used to check the answers twice and thrice, right? I used to check my answers twice and thrice to make sure it's correct. Now the problem with doing that is that you might be getting marks, but you are wasting a lot of time. Please don't do that. You can, reserve the last 10 to 15 minutes to cross-check your answers again, but don't do it in the examination while you're writing it, while you're giving your exams, while you're writing the answers. Don't go back to the previous one to check whether the answer written is correct or wrong, because again, that's second guessing your abilities would end up wasting a lot of time. And the worst part of that is the answers that you recheck again and again might be like for 2 marks or 3 marks, or that's pretty much it. So don't waste your time, a lot of time, on those kind of questions, going back to it over and over again and cross-checking it and wasting your time. Yes, complete your paper as soon as possible, in the sense, try to do it at least 10 to 15 minutes before, so you have enough time to cross-check your answers, and if there's any mistake, you can check your calculations and get it sorted right there and then. So please make sure that you do that at least 10 to 15 minutes before. And apart from that, good luck. All right, stay confident and keep smiling. Whatever happens for good. Don't I would say, don't feel bad. All right, whatever happens, whether it goes good or bad, please remember that that's not the end of your life, and it's just another exam, right? You've given so many exams in the past, like all the way from your LKG, UKG. From LKG, UKG, you've been giving tests, right? School test, class test, periodic test, that test, this test, surprise test. You've been giving tests your entire life. The one thing that you have done so many number of times, that you have done it again and again and again and again, is give test. And this is just another test. Your entire life you've been preparing for it. So give your best. All right, that's all. Whatever it is, you need to be proud of your abilities. You need to be proud of how much effort you have put in. That's all that matters. All right. So once again, all the very best of luck. Catch you guys in the next one. Let me know how your math exam went or how it turns out to be. And until the next time we meet, this is Anoop signing off for the day. Take care. Good luck. And do not forget to check out Sana Ma'am's session, where she had actually taken up a lot of doubts. So something maybe that you wanted to clear up, you can get it cleared in the marathon series. The whole marathon series has been put up. So before you go to bed, check it out. And, you might find some important questions there. Mark it, practice it, and give your best. All right. Until the next time we meet, this is Anoop signing off. All the best. Take care. Peace. Good luck, guys. Take care. See you soon. Bye-bye.